Hello everyone and welcome to the Midas webinar for post-tensioned box girder bridges. My name is Adam Kane and I'll be taking you through proceedings today. First of all, I want to do a quick sound check, and so if you could please raise your hand in the room or place your comments in the GoToMeeting dialog box, that'd be brilliant. Okay, I'll start in about 10 or 15 seconds. We've got quite a few people in the room raising their hands, so I know you can hear me now, but I just want to wait a couple more seconds for a few more people to enter. Okay, let's begin then. So my name is Adam Kane, I'm part of the technical support team for Midas in the UK, based in Hammersmith. There's if you want to contact us, there's a few of our details on the screen there. Excuse me, and we'll just make into proceedings. Right, just going to go through some of the housekeeping rules for GoToMeeting. If you can hear me or I'm slightly muffled, then you might have your computer volume set to mute or quite low. If you want to maximise the screen, just press the two boxes overlapping each other. And if your screensaver happens to kick in or your screen does go blank, then it's more than likely to be that. So if you want to constantly either wiggle your mouse or go set it to off now in the settings. So just a little bit more about the GoToWebinar dialog box. If you want to minute it so it just becomes the small strip, then just click on the red button. If you want to post your questions, then please put them in the dialog box. We've got a technical support engineer on standby, so we'll be able to answer any of your questions. So just go through the contents. First of all, I'll give you an introduction, and then we'll just go through the basics of post-tensioning, the method of construction, box girder bridge example, prestressed tendon definition, time-dependent material behaviour, analyst results, camber calculations for erection control, and the design text of Eurocode. So we have got a lot to get through. We are going to try and squeeze it into the 30 minutes, but it is likely that it's just going to slightly roll over. Excuse me. So just to give you a brief introduction, so first of all we'll talk about the need for the post-tension box girder bridges. High torsional resistance of box sections, which is beneficial for the horizontally curved bridges essentially, so it's in the tension as well. So the material cost cutting and the post-tensioning leads to reduction in the concrete member size and the rebars. This is because the steel is in tension, and that is basically pushing the concrete into compression, where we all know that concrete and compression and its material properties rely on that anyway, so it's basically saving on the material used. You've got an lower overall maintenance and life cycle cost for the structure. This is obviously if you do carry out the construction properly, i.e. grouting and everything's done in the appropriate manner. So that relies on heavily monitoring of the actual site when it's being carried out, but this is a low maintenance cost if it was all done properly. Higher ultimate strength due to the bond generated between the strand and the concrete in both compression and tension, so basically that grouting of the cables and the interaction between the steel that's in tension and the concrete that's in compression. And you've got the full section utilization, and it keeps down on the crack control as well, because obviously it's all in compression, and we'll go into that in a bit more detail. So this is today's example. We've got 3 spans, and they will be going in as 3 spans, so you've got 40 meters, 45 meters and 40 meters again. Obviously you can see all your boundary conditions there, and we've got the width of the bridge is 8.5 meters, and then you've got all the effective width and everything like that. 1.5, 1.4 and 1.5, so it's a 2-lane structure. And we'll just continue now into the presentation. And just to add, this is the full staging method we're going to be carrying out during this example, and what we're going to be showing you. So the tendon strands are pre-stressed or tensioned to apply pre-compression on the concrete, leading to effectively zero tension on the concrete section, thus eliminating the cracking and increasing the ultimate strength of the section itself. There's 2 methods of pre-stressing. So pretensioning, which is the pre-stressing tendons, is applied before the concrete is casted, commonly used for precast beam bridges like M, Y, TY, U beams, etc., things like that. So the most often these tendons are straight tendons, and bridges are most single span bridges with span lengths ranging to about 20 meters at a maximum. So post-tensioning, which is pre-stress, is applied after casting of the concrete, which is used commonly for voided decks, box girders, and can cater to long spans, and this is basically spans of more than 30 meters, and in situ concrete construction, etc., and things like that. So we do to with the construction stage. So in the figure you can see at the top there, you can see the effects of the pre-stressing a simple supported beam. Without pre-stress, it will have a sagging profile with tension in the bottom fibres. Pre-stressing in the bottom fibres leads to additional compression in concrete and eliminates the tension of the overall beam in hogging. So for continuous spans where you have continuous sagging and hogging profiles of bending, we give a curvature to the tendons, such that near supports the tendon is at the top fibre, and at the end or in the mid span it's in the bottom fibre. So there is additional compression at the top to mitigate any existing tension near the supports. So for the post-tensioning, is when the post-tension is applied, it's to do a casting of the concrete with the ducts in place. So as you can see illustrated, there is the actual duct. You've got the placement of the tendon, as you can see from the second image, just down, and then you have the anchorage blocks placed at either end. What happens then is obviously you can either tension, you can jack it. When I say jack, is putting it in tension, is actually acting against the concrete and putting that in compression. So you keep on jacking it. You can either jack it on one end or both ends, and then you just basically cut the tendon at the edge. Once you've carried out the sealing and any grouting that's going to be taking place, you can cut the tendons, and then what this will happen is, if it's actually grouted in the ducts, then it's a bonded tendon. So what will happen is that when you've cut either end, then it will actually put the tendon, it will be fully in tension, and it will put the concrete itself fully into compression, pushing either end together. So now just going on to prestress losses. Prestress losses are critical for the analysis and the correct tendon force to be applied. So sometimes, if you have dealt with it before, you can get up to 20% losses in the tendon profiles, or get tendon losses 20%. They're basically two categories of losses. So you have the short term, and two, the long term time dependent losses. So just talk briefly on short term losses. When the elastic shortening occurs primarily in the pre-tensioned or precast beams as shown in the figure below, and when the concrete is casted after pre-stressing has been applied, the concrete shortens due to the pre-compression, which leads to the tendon shortening, that leads to the loss of the tendon stress, and that's what we're talking about, the tendon losses. So just going on to friction and anchorages, loss occur only in post-tension tendons. As soon as the tendon is cut and pre-stress is transferred to the beam. The image shows a typical post-tension tendon with a curvature. So friction loss occurs due to this curvature. In unbonded tendons, there will be friction loss due to wobbling. As from this image here, you can see there's always a slip loss in the tendon near the anchorage, which reduces the tendon force furthermore. So as you can see, it actually tailors off, and that's where you're getting your loss after it's been cut. So just looking at the elastic deformation loss, so during the construction of a box girder bridge, many times we come across sequential post-tensioning. This can lead to elastic shortening losses in the tendons that were post-tensioned earlier in the actual construction. So as you can see in the figure here, so tendon 1 is tensioned first, and then tendon 2 is tensioned after, and what will happen is that in tendon 1 you'll get losses because of the tension being carried out in tendon 2. Now we're going to look at the finite element analysis software, so it's going to bring that across now. So in the works tree you can see that I've already defined the actual some of the materials and the tendons. So now we're just going to look at the actual tendon profile. So look at the tendon properties, then just go through it. So we've already got defined there. Just go to the modify tab and just show you a few things. So we can look at it in the pre-tension and post-tensioned. You can also look at the external as well. So we're going to look at post-tension today. We can select the millimeters or the material. So you can just select the strand diameter and the number of strands you want. We can also select the relaxation coefficient. So this is when the steel is stressed for a long period of time, it undergoes relaxation, which leads to the tendon force loss. So we can look at all the different codes, we can select them. We're going to look at the Eurocode today, and you can look at it if you want it to have depending on what material you want, so it can be hot rolled or it can be ordinary or low, so the material properties. You can set the yield, you can also look at the curvature friction factor, and we can even look at the wobble friction factor as per the code. So you just go into the Eurocode and select it, and we can look at the Anchorage slip and just give it the amount of millimeters, and we can look at the bonded and unbonded length. So we're going to be looking at bonded in this example. Let's close that. So we just want to look at the actual the wizard. We're going for the full staging method, so we're just going to pull that up. As you hear, you've got the dialog box appears, and we can change any of the parameters. So we just want to give it the length of each part of the bridge. So it is going to be 40 meters, 45 meters, and 40 meters. Those are the 3 spans. So we can change the different sections, and we can look at the different drawings as well. If you did want to have it tapered, then we could actually do that. But we're just going to focus on the straight bridge. So here's the tendon profile in the next tab. So we can look at just the tendon one. We can look at the jacking stress, and that's all as per the code as well. Okay. So I see the bridge has been created, and all the construction stages have been created as well. So we just look to the side, and we can look at all the boundary conditions. They're all on there. I'll just show you those quickly. So those are the boundary conditions, and we've got all the different different load cases and the tendon profiles as well. So we can visually look at the tendon profiles. You can also look at where the section changes when it goes over the actual piers of the structure. So hang on, I've just got to swivel this round a second. There you go to the front, and as you can see, it changes the profile as it moves across the different sections. So now I've got in the side view, I just want to freeze that view and then just go through the construction stages. So let's flick through those. So there's the first section, second section, and the third section, and the tendon profile is being developed as it goes throughout. So we just go back into the base mode. So now we've just gone through the modelling, just going to go straight back to the presentation, and we're just going to go through creep and shrinkage. So just go and talk about creep and shrinkage. Creep and shrinkage is the deformation with time under the permanent stress. So creep depends on the Eurocode 2, and these are the is key. It depends on these key parameters underneath. So the compressive strength of the material, the exposed area, and the perimeter of the bridge section, which I'll show you in a moment. The age of the loading, and also the type of cement that's actually used. So this is to do with the hardening effect and everything like that. So shrinkage of concrete is defined as the contraction due to the loss of moisture. So we know this from, if you're on site, then you could have a lot of moisture in your concrete, and then you'll get surface cracking created because of the loss of moisture coming out of the concrete itself. You can see here the creep coefficient. So this is as per the Eurocode. So over the period of time, then the creep coefficient will change. You've also got the shrinkage as well over time. Right, so creep deformation leads to shortening or elongating of tendons, which results in loss of pre-stress. Similarly, shrinkage also affects the pre-stress as well. And now in return, dead loads, pre-stress and shrinkage affect creep. So this is a cycle, and it's a very complicated thing to solve numerically, as in by hand. So this is why finite element analysis softwares have become more aware of this, and they actually solve it a lot faster. So now we're just going to go back into the program. I'm going to show you some of the creep and shrinkage coefficients that we can generate. So just go to the properties and then creep and shrinkage, and I'm going to create a new one. So just select the code, give it a name. I'll just creep a minute. So just the Eurocode, and we can give it the characteristic strength. So just give it a number, so 50. Then we can look at the size of the member, or notional size of the member. So that's going to be a meter, and just want to do it's going to be a concrete bridge as per Eurocode 2. And we can look at the different types of cement as well, so you can give it class S, class N or class R, depending on what you're doing. And we can also specify the age of the concrete from the beginning of the shrinkage, so we just want to set that to 5 because that's the age of the segments before they go into place. So and that is the creep coefficient that's been created, so the program automatically does that, and also the shrinkage strain as well. So over the amount of days that the actual bridge is in place, you'll see as it changes the creep coefficient and how the program takes that into account as it's doing the calculations. So that's been created, so just go back into the actual presentation itself. So now just looking at the compressive strength gain. So with time, concrete gains the compressive strength, and the modulus of elasticity also increases as per the Eurocode 2. And this is the actual calculation for that compressive strength gain increase. And there's the curvature on all the graphical representation there over time of days. So as you see, we've got 50 megapascals, and it will take 28 days to come to that hardening point. So this is all based on the age of the loading and also the type of cement that's used. So just back into the software now. What we'll do is go back to and look at the actual compressive strength. So we'll just give that a name, strength, and I just want to give it as per the Eurocode and actually the strength of the concrete. So just make it 58, and then we'll just draw the graph, and as you see over the 28-day period there, and that's been created. So now we've got to link those together. So we're going to link the materials to the material properties within the working space. So we just add that, and that's basically linked the concrete that's been used in the model with the creep and shrinkage effect. So now we see the external post-tensioning. So the pre-stressing is achieved by elements located outside of the concrete. The tendons can lie outside of the member, as I'm sure you're all, or some of you are aware from reading the NCE and different articles, that the Hammersmith overpass is actually this is going to happen on it, or it's supposedly going to happen. So the used for strengthening, these are basically the tendons are used for strengthening of existing bridges, or so they're added to the inside source, and the tendons are draped deviators, and the deviators are indicated here. So what will happen is that these can be fixed to the inside of the pre-stressed concrete member, and then you tension up those and it actually adds strength to the bridge. Now I'm just going to look at the secondary effects of post-tensioning. So secondary effects are caused due to indeterminacy in the structure, additional reactions generated at intermediate points or supports, which lead to secondary forces. This happens whenever the tendon profile is restrained at some point in the structure. So in the finite element analysis software, then the primary pre-stress moment and the secondary pre-stress moment are considered, and they're also taken into account basically. So to give you the total moment, total pre-stress moment. So now we're just going to go through the different construction types of the box girder bridges. So first of all, we'll just focus on the balance cantilever method. So here we have it. You see in the diagram there, the piers are constructed. The box sections over the pier, or the pier table as it is known, is constructed, and box girder segments are added to either side of the pier table. They're effectively balancing each other out. So during the construction, the segments together behave as a cantilever supported at the pier table location. So just to move on to the incremental launching method, you can see the nose there. So an innovative method where the piers are very tall, so they can be extremely high. The construction is done with the help of a launching steel girder, also known as the nose. The segments are cast in situ, and as the segments are casted behind the launching girder, they are pushed by a sliding mechanism from one abutment to the other. It's a quick approach for straight bridges. It can't be really used for curved bridges because the actual nose is dead straight, like an arrow effectively moving from one end to the other. So the movable scaffolding system, which is the next method, the scaffold moves as it builds one span at a time. A quick approach for straight bridges, but at each construction intermediate pier there's always a rather large end reaction of the movable scaffolding. Effectively the scaffold is quite large, and then you've got a large amount of concrete that's being dumped on the pier itself, so it creates a massive moment at that point. So that's all the wet concrete of the as the wet concrete is being cast for the next span. The full staging method, which is very suitable for horizontally curved and for piers that are not very high, so you can actually create the scaffolding and build them up to that level. So now we're talking about the full staging method, and as you can see we've got a video at the top there illustrating this. So what it is focus on the dead weight of the concrete, the formwork and the false work, which are fully shored or staged over the full spans of the bridge until the concrete gains a certain level of strength. So as you see from the diagram there, that the scaffolding is put in place, all the tendons are put in place as well, and then the concrete's cast, and the scaffolding is left there for a number of days until the actual hardening process takes place, and then it is all removed. So although the shored full staging method assumes the effect of the supports is negated by the post-tensioning. So now I'm just going to show you how we do this in the software, how we handle it. So just to bring the working space again, so finite element analysis software. So first of all I just want to show you the groups and all the different construction stages that have been created, and we've got, as you see there, it's highlighted in red going across the different groups that have been created. We've also got the boundary conditions as well for all the different piers, and we've also got the different load groups, so these are all created. Just look at the tendon pre-stress, and we're going to look at the jacking forces we can put in place. So we just select one of the tendons and the load groups, and we can just select one of the tendons or the construction stage, and we can select which end we want to jack, so be it the beginning, the end, or both at the same time. So as we select the beginning, we'll give it a value, so say 15,000 or 1500, and then we just select the grouting. So after, we want to do that after 1 day, or just one step. Just add. So that's one of the tendons that's actually been done, or the jacking force has been placed into it. Now we'll just show you the actual different construction stages. Let me just go to modify. As we're just going to go through the different construction stages and show you what's in each one. So first of all, we'll start off with construction stage 1. The duration is 20 days, and we've got the actual that is the construction stage. It's got an age of 5 days, and the total duration of the section will be 20 days until the next section is put in place. So we go on to the construction stage 2, and then we can look at the boundary conditions and the loads. So look at the boundary conditions, we've got the and also the loads as well, and that means that's the tendon profiles there, and those have been put in place. So we go through the construction stage 3, and as you see, more tendons are being added, and then construction stage 4, whereas all the boundary conditions and all the loads have actually been applied, and then we're just going to give that a duration of about 10,000 days. So that would be that we can, when we do the tendon profile losses, then we work it out over a long period of time. So this will take into account the creep and shrinkage effect. So now that's been done, just go straight back into the presentation and take you through the rest of it. So we just look at the post-analysis results. I'm just going to take you through what we're going to take you back into the program, but I just want to take you through now what we're going to cover. So we're going to look at the prestressed tendon force variation with time, and then we'll look at the box girder stresses under the service loads. We'll look at the pre-camber calculation for erection control, and then we'll look at the tendon stress limit checks and the post-tension box girder fibre principal stresses and shear stresses. We'll just go straight back into the software and show you it there. So here we've got the modelling space. So I just want to take you through some of the beam diagrams and look at the different construction stages. So just to flick through them, so we can look at the beam diagrams for each construction stage. So here we have all of our different dead loads and reactions and all our different load cases. So one of the key things is the tendon primary, and we can look at the tendon secondary as well, and the creep secondary and shrinkage secondary. So what we're going to focus on first is the dead load. So what we've got, put the MY, and we just want to look at the legend, and we just click apply. We just put it in solid, sorry, hang on, there you go. So now it's in solid. Now we can just flick through the different construction stages and see the bending moments and as they're happening, and go all the way through to the fourth stage. So just stay on that stage now. Then we can look at the tendon primary, and as you can see it's the opposite, and which is the way it should be, because it's the actual trying to create that hogging moment. So now we look at the tendon secondary, click apply, and we can look at that for all the construction stages as well. And just to go on to look at the summation, which is all of the loads all added together. So there you've got the summation of everything, and we can look at that from the side view there. Now just go on straight onto the bridge girder diagrams. So we're just going to focus on the last step and also on the summation. Then we can look at the bridge deck, we look at the combined components, and then just click apply. What we've got here is, so you've got the compression at the top, and tension at the top, compression at the bottom is what I was meant to say. Then you've actually got the curve there. So this is the actual stress, and those are the allowable stress lines on the outside. So just going back to the model, now we're going to focus on the tendon loss graph. So what we got here is one of the tendon profiles, and you've got the tendon loss there at the start, and the actual value, so it's 1,900 kilonewtons. And what we can do now is put it through the different construction stages and animate it, and as you can see that it's got a drop of about 200 kilonewtons in the fourth stage from the first stage, which is a drop of about 10%. So you see here, this is the anchorage loss has been created at the start, and that's when we were talking about when we actually removed the ends when we cut the tendons. So we're just going to look at the results table and look at the tendons, or the tendon losses, and as you see here we can go through the different construction stages, and we can also see from the top, so you can look at the stress, the elastic deformation, you can look at the creepage shrinkage loss, and you can also look at the relaxation loss. Then finally you can look at the stress, and as you can see that it's at 91% of the capacity by the fourth stage. So let's go back into the model. So now I'm just going to show you the camber and the reactions. So just go down to generate the camber. So just going into the general camber control, I just want to briefly explain what the camber angle is. Now the camber angle is created as each additional segment is added to the bridge, so that extra weight is creating a forcing moment going down. So that means that you've got to react to that actual moment that's being created by creating a camber angle angled up. So this means that you could have it during casting, or you could have it during the actual precast units being made by the manufacturing plant. So we're just going to focus on this now. So we're just going to look at the construction direction. So you've got in the plus DX direction, and now we're just going to look at the general section, the graph view, the graphical representation of it. So this is doing all the summations. So what I'm going to do now is I'm going to show you two different graphs. Now this is the general manufacturer's Camber, so this is the precast section camber angle and how that is going to be manufactured. And the other graphical representation I'm going to show you, so this is the actual cast in situ camber angle that's been created. So it's giving you in millimeters at the bottom there, the actual camber angle that's been created. So the key thing for the design engineer is not necessarily the construction of it. So really this isn't for the design engineer, it's more based on the construction activity that's going to be carried out in the field or in the manufacturing plant. So it's very key for it to go there in detail. It's going to go back into the presentation now and just go to the post-tensioned concrete design, to Eurocode 2. So basically going to focus on the ultimate limit state, the bending resistance, shear resistance and torsional resistance. Then we'll look at the serviceability limit state, the concrete stress limitations, the tensile stress limitations in the pre-stressing steel, and also the crack width limit check as well. So now we're going to look at the bending resistance. So we just have to basically simply calculate as any other reinforced concrete section. So you see the block at the top there, just indicate that with my mouse. The rectangular stress block can be assumed from the Eurocode, and first principles can be used for the moment resistance calculation, which is illustrated in this rather long calculation here. And what you do is you follow the workflow. So just assume the neutral axis, calculate the FC for concrete, the compressive strength, calculate the FS or the reinforcement, and then calculate the tendons as well, and then you just do the comparison against each other, and then you get the neutral axis with the depth if it's all balanced itself out. So now we're just going to look at the shear resistance. So what I just want to say is the software checks for the tensile stress as it is the governing stress for shear, which is the occurrence in the beam. So I'm just going to hover over that, and we're just on the screen there. From the diagram we can see the strut tie action in the concrete beam with the stirrups, so just illustrating that with the red block. For box girders we take the total web thickness for the shear calculation, so as you can see the box girders there. But first we calculate the shear resistance of the concrete in compression. If that is not sufficient, then we calculate the shear rebar required, so carry out the calculation. So the theta angle here you see at the bottom, where you've got all the compressive chords, the struts, the tensile chords and the shear reinforcement. This theta angle can actually be inputted into the software. So just looking at the torsional resistance, so one of the key advantages of the box girder or the box girders are their high torsional resistance, which makes them suitable options for the curved bridges. Effective areas for torsion is the closed area as shown in the image here. The maximum resistance of a member subjected to torsion and shear is limited by the capacity of the concrete strut. In order not to exceed the resistance, the following conditions should be satisfied. So the calculation on screen is just giving you the condition in which it should be satisfied. So just looking at the stress limitations in concrete, so the combined normal, actual and the bending stress checks and principal stress checks for the box girders, including the normal and the shear stresses. So you can see from the calculation at the bottom there. So the tendon stress limit checks, so the allowable stress in tendons immediately after the anchor set at the anchorages, there's a calculation there. We can do it as per the UK National Annex, and you've got the K factors there. The allowable stress in tendons immediately after the anchor set elsewhere is the UK National Annex, so you can see it has changed slightly. And we can also incorporate the allowable stress in tendon at service limit state after losses have taken place, and there's the UK National Annex there. So just to focus on the crack width limit checks, which is the use of the effective concrete area in the tension zone for calculating the crack width. So just to illustrate that there, and just take into account the exposure class decides the allowable crack width, and you see there at the bottom there, the W max depends on the exposure class of concrete, so the X01, XC1, etc. all the way through. So now I'm just going to look at how the software can handle design, and just going to add some reinforcement as well, and look at some of the shear stirrups and stuff. So just go to properties, the section manager and the reinforcements. So we can look at the section, we've only got one single section going through the whole span, and we can look at the reinforcement, we can also change it as well and manipulate it where we want. We can also see the tendon profiles, we can look at the shear reinforcement throughout and the stirrups, and which can be changed. We can also change the torsional reinforcement, and horizontal and longitudinal reinforcement can be added for the torsional resistance. So just add that there, And so I'm just going to look at some of the design parameters that we were concentrating on in the presentation. So just to open that up, so that's the pre-stressed concrete design parameters to the Eurocode and the British National Annex we've got incorporated in there. And we can look at the strut angle for the shear resistance, and that is set at 45 degrees. Obviously you change that. We can modify any parameters. It's not essentially a black box, so we can just edit it as and when we need it as per the code, depending on where you work in. And we can look at the ultimate limit states and also the serviceability limit states. So what I'm going to do now is I'm just going to show you the Excel sheet that gives you all the results out, and show you the serviceability load combinations as well. So this is the serviceability load combinations. It will automatically separate them out for you, but if you are doing it as per a different code, then you can just put the parameters in the additional boxes yourself. So as I mentioned, I'm just going to now go over to show you the Excel worksheet. There you go. What I do, so all your results come out in Excel format, and you can look at all the different parameters and everything to do with your design that's been carried out as per the code, and all the different moments and everything. I won't go into too much detail in them. I will pick out a few key things. I just hold my mouse. So the minimum shear force there, the maximum shear force there as well, and the torsional resistance, and also got the crack width in the top and the bottom. And we can look at the bending resistance and the positive, negative, the shear resistance and the ith end and jth end of each end of the member, and we also look at the torsional resistance as well. Now we're just going to look at some of the results diagrams and some of the applied forces and also the capacities. So let's look at it in a solid. So the dashed line, or the shaded line, sorry, you see there is the applied force, and the dashed line is the capacity of the member. Now we're going to look at the shear. So as you see, that this is exactly the same scenario, and it's failing in a section, so we'd have to add more shear reinforcements to the sections. And we look at the results tables and look at the shear strength. We'll check the shear strength. You select that. As you can see there, you've got all your values and everything. You see where it's failing because it's highlighted in red as per the code. And that's all our different values there. So I just take you back to the presentation and to close. So challenges in the pre-stressed concrete bridges. You need, like we mentioned at the start, where we've had a lot of bridges fail under this construction method, you need highly skilled construction teams which are required because of the anchorage systems and the grouting methods that are used. So if moisture gets in there, it can create corrosion of the steel cables that provides the post-tension for the box girder bridges, which become a major concern because then you can have catastrophic failures of the mechanisms holding the bridge up. It can become costly because of the high strength materials and equipment for the construction, i.e. the formwork that is used, and also the grades of the steel that you're using as well. So just to talk about the general workflow for the analysis, I'm just going to go through the step by step. So the primary design, or the span information and the alignments, and then you can move on to decide the methodology of the construction that's going to be taking place. So be it your incremental launching method, your balanced counter method, or your full staging method. So any of these can be adopted. So the choice of pre-stressing tendon profiles based on the construction approach. So for the full staging method, we basically have continuous tendons. For the balanced counterlever method, you'd have discrete tendons. So we can build the construction stages with the time dependent materials, and we can take them into consideration. We can check the losses, then we check the losses in the tendons, then we check the stresses in the construction stages throughout different construction stages. Then we'd apply the live loads and other loads to the bridge, i.e. our moving loads and everything like that. Then we can perform the ultimate limit serviceability checks and the stress checks under the service loads. Then we move on to check the camber angle required for the erection control. thank you for listening, everyone, and we had a good turnout again today, as always, and thank you for always turning up, and it's been a pleasure to actually have these training sessions. We've now come to the end. We might have one in a few weeks' time, but we haven't got any scheduled in terms of the webinars that we're going to be participating in, but hopefully we'll be able to pick up maybe in the new year and carry on with them. My name's been Adam Kane, and please obviously go onto YouTube or any of the mediums that we've got out there, and there's always extra learning, and we're always keen to teach. So thank you for your time, and I will be seeing you soon. Thank you.